Welcome to the second of the quantum materials seminars this month. It's lovely to see so many people here. My name is Helena and I am the Quantum Materials Outreach Officer at the Department of Physics. So without further ado, I'll introduce our seminar speaker today, Johnny. Johnny is a DPhil student here in the Quantum Materials group. For those of you who don't know, DPhil is basically what Oxford calls a PhD, so the degree that you do after you've done your undergraduate and master's degree. And he is going to talk to you today a little bit about his work and how he uses muons, so something more associated with particle physics, to study what goes on inside these wonderful quantum materials and what we can use this for. So without further ado, I'll hand over to Johnny. There you go.
Thank you very much, Helena, and hello everybody. As Helena said, I'm Johnny and I'm a DPhil student doing Condensed Matter Physics at the University of Oxford. Now, this presentation is essentially going to be like a short infomercial, if you like, where I convince you that muons are the coolest particle that we know about and that we've discovered so far. Now, muons take us into a world where a lot of the physics you do at school, even some of the really basic stuff like speed being distance divided by time, it doesn't quite work anymore. And instead, we have to look to some of the strangest and wackiest theories that have been discovered over the last 100 years, that of Einstein and Schrödinger, to really get an understanding of what muons are trying to tell us about the universe. Now, as Helena mentioned, muons normally belong in the realm of particle physics, and particle physics is sometimes a little bit controversial. Headlines like this are normally quite common about CERN, the big particle accelerator in Switzerland. They've got a plan for a $10 billion particle accelerator, which is going to be 4 times the size of the current one. Now, $10 billion does sound like a lot of money, and there's also seems to be some quite negative side effects of them as well. There's reports we might be able to unleash hell on Earth. There's reports we might rip the fabric of the universe. There's reports we might accidentally summon God, and we might even shrink the Earth to the size of 2 football pitches. So a question you might have then is, why bother? Why put in all this money to essentially shrink the Earth to the size of 2 football pitches? No, surely it's not worth it. Well, I suppose if you like, I'm here today to convince you otherwise. So let's start off then with what a muon actually is. So the best way to think of a muon is to cast your mind back to an atom. So atoms, as many of you know, will have protons and neutrons in the center forming a nucleus. The protons are positively charged and the neutrons have no charge. And then you have these electrons here whizzing around the outside. Now, a muon fits into this by essentially being the same thing, if you like, as an electron in most of its particle physics properties, but it's got 2 important differences. The first is that it's 200 times as heavy. It's about 200 times as heavy as an electron, so it's about 10% of the mass of a proton. And crucially, it only lasts for 2 millionths of a second. And 2 millionths of a second does sound really, really fast. And it is really fast. You know, if something flashed in front of you in 2 millionths of a second, you would never notice it yourself. But don't forget, your computer has a processor that runs at a gigahertz clock speed. That means it's doing some sort of calculation every billionth of a second. So actually, measuring a muon being born, if you like, and then decaying, you know, in a millionth of a second, that's absolutely easy. It's really easy for modern electronics to be able to cope with. And for those of you who have done particle physics, and if you haven't, don't worry, this is what is called the standard model of particle physics. And this is, if you like, the periodic table of particle physics. So whereas the periodic table tells you all the possible atoms you can get, this tells you all the particles that you can get. And like the periodic table, if 2 particles are close to each other in this, they share a lot of the same properties. And you can see here the muon sits right next door to the electron. Okay, so whenever I say muon, if you like, in this presentation, just think heavy electron. Okay, you don't need to think of it in any more detail than that. So we're going to start off our story then with the discovery of the muon. And our story of the discovery of the muon starts off in 1910 with this man here, Theodor Wolff. Now, Theodor Wolff was a Jesuit priest, and he became a Jesuit priest when he was 20 years old, so very, very young. But later in life, he switched to physics, and he built this little device here called an electroscope. And what an electroscope does, it measures charged particles in the air. And he found that when his electroscope was sitting on his desk, it was always measuring a background. There was always a background of charged particles. A bit like when you get your Geiger counter out in your labs at school, there's always a background there, even if you haven't put a radioactive source right next to it. Now, at the time, this was assumed to be all coming from the Earth. So Theodore Wolff decided to test this out, and so he got his electroscope and took it to the Eiffel Tower in Paris. And he did a reading at the bottom, a few readings coming up, and a reading at the top. Now, the idea behind this was that if all the radiation background was coming from the Earth, as he went up, there would be less radiation, so his thing would read a lot less. Now, his electroscope did measure a lower reading, but nowhere near low enough. And it was concluded by him then the radiation can't all be coming from the surface of the Earth. There must be some other source. So a year later, Victor Hess, who was, I think, an Austrian physicist who had to later flee to the United States later in life, he ascended to 5.3 kilometers in a hot air balloon, which is incredibly, incredibly high. 5.3 kilometers is about half the altitude that an airplane flies at today. And he had to do all sorts of things to his instruments to make sure they could withstand that kind of altitude. And he went up that high essentially to see if this trend continued. And what he actually found was that after he went above about a kilometer, there was even more radiation. And a few years later, he received a Nobel Prize in 1936 for his discovery of cosmic rays. That's what he was measuring, and that was the reason why Theodore Wolff's electroscope wasn't measuring particularly low readings as he was going up the Eiffel Tower. And I also point out here that sadly, our good old friend Theodore Wolff wasn't also a recipient of this Nobel Prize. It was sadly only Victor Hess. So, cosmic rays. So cosmic rays essentially are flares of particles which come from the stars and all over the universe, and they smash into the atoms in the Earth's atmosphere, and from this smashing, if you like, creates lots of other little particles, including muons. You can kind of think of it as having like a big particle accelerator up in your head. And we haven't shrunk the Earth to the size of 2 football pitches just yet, so I think we should be okay. And this here then is a picture of the first muon track. So what this is a picture of something in a cloud chamber. And a cloud chamber essentially is something that particles go through and they leave tracks behind. And by analysing these tracks, we can work out what these particles are. In particular, we can work out the ratio of their charge to their mass. And this little bent track here is, I believe, the very first track of a muon. So that's what a muon looks like. And I've done a little animation over it so you can see a bit clearer. It's not particularly clear because this was 1936, but it's still brilliant nonetheless. Now, we're all physicists here, and physicists like to do calculations. So there's 2 numbers that we've talked about. First, muons are created by cosmic rays, by atoms smashing into the atmosphere. And then that happens at about 30 kilometers above sea level. And they last for 2 millionths of a second. So knowing that we can measure them and detect them on Earth, we must be able to calculate their speed. So you all have calculators on your computers or whatever device you're watching this on. A poll will appear on your screen shortly. I want you to try and calculate how fast you think a muon goes using these 2 numbers. You might want to write them down because I think the poll might cover them up. And so I want you to calculate that and put your answer in the poll. And I'll give you about 1.5 minutes for that. There you are, the poll's on your screen now. Brilliant. Okay, so if you want a hint as to how you might think about calculating this, it might not be right. Cast your mind back to speed being distance divided by time, maybe. Okay, brilliant. So I think we've got lots of answers there, and the most popular then is 14 million kilometers per second, which is brilliant. So let's use speed equals distance divided by time. What we can do 30 kilometers divided by 2.2 millionths, and we get 14 million kilometers per second. Sounds quite big. Let's put that in context then. So this here is a scale of speed along the vertical axis. So let's think of fast things. We can populate this grid and we can see whereabouts the muon will fit in with things that we know the speed of. So, first thing you might think of as fast is a car on a motorway. A car on a motorway goes about 110 kilometers per hour, which is about 0.3 kilometers per second. Not really very fast compared to 14 million. Next thing we can think of is maybe the speed of a bullet. Well, that's only 1 kilometer per second. Nowhere near 14 million. What about the speed of the Earth around the Sun? Well, that's only 30. Well, so if we go out a bit more, let's think of cosmic expansion. That's only 100. So what about the speed of light then? Surely nothing can go faster than the speed of light. That must be more than 14 million. But it turns out it's not. So what have we done? Have we managed to calculate the fact that the muons must travel faster than the speed of light? And the answer is no. Nothing can travel faster than the speed of light. It actually turns out that muons are traveling so fast, we have to use the ideas from Einstein's theory of special relativity. And what Einstein tells us is this: muons are traveling so fast when they are born in the atmosphere, and when they are detected on Earth. They're traveling so fast, the distance they see isn't 30 kilometers. It's a lot smaller. This isn't optical. This isn't no matter of I'm going so fast that I'm going to get to my destination quicker. This is a matter of distances themselves are shrinking. Now, unfortunately, I don't have time to go into great detail about this as much as I'd love to. So if you do want to know more, I'd recommend this book here, How to Teach Relativity to Your Dog by Chad Orsel. It's a really good book. I read it myself when I was in year 12 about to study physics at university. I strongly recommend it. Okay, so now this takes me on to my second cool thing about muons. This is muons as spies. So don't forget, muons are very similar to electrons, and electrons make up a lot of the materials that we, all the materials that we use. Now, muons have this special property, which means that when they see magnetic fields, they start to spin round. And the stronger the magnetic field that they see, the faster they spin around, which is really useful. So by measuring their decay products, we can work out, so we can go back in time, we can work out how fast the muon was spinning. And from that, we can determine how strong a magnetic field that the muon can see. So this here is an animation of how it works. So we get, a random structure of atoms. We fire our muons into them and they spin round. And the stronger the magnetic field that they see, the faster they spin round. And after 2 billionths of a second, they decay into their electron-like particles. And from measuring that, we can determine how fast the muon was spinning when it was alive. And from that, what the magnetic fields are doing inside the material. And here's another animation of how it works. You can see here, so this purple arrow here is the muon spinning round, and it's we're applying a field into the board here. And these F and B are just 2 detectors which measure the decay products. And this is what real data looks like. So you can see here, it looks a bit like a sine or cosine wave. And the frequency of that, when we calculate the frequency of that, we can work out the magnetic field that we're applying or more importantly, the magnetic field that the material is seeing. Okay, so I'm afraid because of time, I haven't got time to show you all this. If you want to know, ask a question, I suppose. So one of the main uses of this then is superconductivity, and superconductivity is a really, really cool phenomena where if you get some materials, if you cool them down below a certain temperature, and this temperature is a property of the material, if you cool them down below a certain temperature, they have zero electrical resistance. If you feel your computer at the moment that's running this, you can probably feel it's getting quite warm. That's all because of this electrical resistance. It actually creates a lot of wasted energy. With superconductors, doesn't happen. No wasted energy through heat at all. Now, there's another, this was actually an equivalent thing that superconductors do, and that's that they they expel all magnetic fields you apply on them, which makes them really useful for various applications. One of them is maglev trains. You can use them, so this here has a superconductor on the track, and the whole train is hovering above the tracks. There's no friction between the wheels and the tracks. MRI scanners, some of you might have looked at MRI scanners in your courses so far. MRI scanners need superconductors to create the really, really high magnetic fields to create the, to allow the nuclei to resonate. So how can muons help us to understand superconductors? So remember, muons can help us to measure magnetic fields. And muons, what was I going to say? Yeah, so muons essentially spin around in a material, and the faster they spin around, the stronger the magnetic field that they see. And I've mentioned already before that superconductors work by expelling magnetic fields. So this here is what the surface of some superconductors looks like, where the bright lights essentially are the magnetic fields. So the brighter the light, the stronger the magnetic field. So what we do here, we fire in a muon. Wherever it sits, it spins due to the magnetic field that it can see. So here it can see the magnetic field through this vortex here, so it's going to spin really fast. And through measuring its decay product, we can calculate how what the magnetic fields are doing inside the material. So that brings us to the end of the talk. And there's one final thought for you. All I've talked about today is what this one particle can do in this quite big grid of particles and forces. Now just imagine what's going to be possible when we learn how to harness the rest. Okay, and that concludes my talk. Thank you very much for listening.
Fantastic, thank you very much for that. That was fascinating, Johnny. So we'll now go on to our Q&A portion. So get asking your questions. Type them into the Q&A below. We've already had a few coming in, which is great. So the top one at the moment is an easy one to start off with. People are curious about what's your Zoom background?
Yes. So this is the EMU spectrometer. So if you look at this slide here, those F and B portions there. So F and B essentially corresponds to, wait, I've got a better photo on here somewhere. There we are. So this is essentially what we use to detect the muons. So these silver parts here are what detects the decay products of the muons. And when the muons come in, they come in from behind the screen, and they stop in the material, which is behind this little round gold bit there. And yeah, that's what we use to measure the muons.
Awesome. It makes a very impressive background as well, I have to say.
It's great.
Okay, cool. So another question here. Are muons fundamental particles?
Yes, they are. Yeah. So as far as I'm aware, so far we haven't found a way of splitting them. So a muon is about as fundamental as you can get. It's just like electrons.
Nice. Obviously, it's all the theory, isn't it? The standard model. It's still considered a theory, so we might find that they're not fundamental. That's the beauty of science.
Exactly. Yeah. You never know. You know, I think it's when you become, complacent, if you like. We've always found through history when you get complacent that we know everything. Something crazy gets discovered.
Yeah, exactly. Cool. So we've got a few questions about superconductivity, which you went into briefly. So someone's mentioned quantum locking. So they've heard that in relation to superconductivity. So could you maybe tell us a little bit more about what that means?
So I think by quantum locking, I think you mean what we're seeing here. So this is essentially the, it's a bit difficult to explain, I'm afraid, but if you look at the surface of a superconductor, it's essentially the magnetic field is being channeled through these little vortices on the screen there. And that essentially keeps things in place. I think that's the best way I can think of explaining it.
It's the sort of thing where you need to kind of have a little bit more knowledge of quantum physics, right?
Yeah, and if you were doing this like on stage, I could get out the superconductors and demonstrate things with you, but unfortunately,
yeah,
I'll do that. Sorry.
No, that's great. It's still a fascinating topic, even if we can't see it done in person. The fact that an object can levitate over magnets is pretty special.
Yeah, it's fascinating.
Cool. So we've had one question here. Would anti-muons behave differently?
Brilliant question. So there's actually one thing that I've glossed over in my talk quite a lot. And the fact is we actually use anti-muons more than normal muons. So normal muons, essentially, non-anti-muons have negative charge. And the problem with negative charge is that they're just like electrons. So if you get a negative charge and chuck it at an atom, it'll interact with the electrons a bit too much. So actually trying to make magnetic measurements will be a big pain. But if you use anti-muons, they're positively charged. They're actually a lot more similar to protons when we measure magnetic fields with them. So you might have noticed here in these these animations, I've used mu plus because actually we're really talking about anti-muons here, and the mu plus decay into positrons, which are actually the particles that we normally detect. You can do this with normal muons as well, but it's a lot harder to do with normal muons.
Nice. So we're actually using antimatter rather than...
Yeah, which sounds a lot cooler, I think.
It does. Sorry, I had a question there and it's disappeared. Here we go. So going back to when you were discussing relativity.
Yes.
And how you were saying that even though we calculated that they're traveling faster than the speed of light, it's okay because the length contracts, it becomes smaller. So we've got a good question here that asks, when the muons are created in the atmosphere, does special relativity mean that the distance becomes smaller, or does time change?
And the answer is actually both. So it depends what observer you're talking to. So if you are sitting on the muon, if you like, so the distance that you would see from you to the Earth would be shorter. And I've actually got a graph here which I can show you. There we are. So this length contraction. So on the x-axis here, you've got the percentage of the speed of light you're traveling at. On the y-axis is what a 1 meter length somebody else would be to you. So you can see here, if you're traveling close to 0% of the speed of light, like a car going on a motorway or whatever, 1 meter is always 1 meter. Nothing changes at all, as we know. But an Earth would look around. But as we go faster and faster, the Earth appears really flat, and essentially that's what the Earth looks like to a muon. But yeah, there's another effect as well with time dilation. And time dilation is what, if we were sitting on Earth and we had our stopwatch and we were timing how long a muon would take, we wouldn't measure 2 billionths of a second, we would measure a lot more. In fact, I think I worked out you would measure about 5 times as many as 2.2, so about 10 microseconds. So there's actually 2 effects going on. And yeah, I think if you want to know more about that, I think I'd definitely recommend this book. I think it's great help.
Yeah. So if you want to just leave that slide up for a second so people can note down the name of the book if you're interested.
Definitely.
I mean, any title of a book that's about how to teach relativity to your dog, it's got to be fun.
Yeah. And I've seen somebody else ask what other books I'd recommend. There's another book which I also read called How to Teach Quantum Physics to Your Dog by the same author. Also really, really good. I think a lot of quantum physics books tend to introduce you to the really weird stuff before actually kind of introducing you to the more tame side of it and more understandable side of it. But I think these books are really, really good at striking a balance between getting you excited about the weird stuff, but also, giving you a good understanding of what's going on.
Which is exactly what you need.
Yeah, definitely.
Actually try and understand what's going on with all of the weird and fascinating things. I've just seen one fun comment on what you were talking about before when we were talking about the length contraction. So essentially the Earth is flat.
Absolutely, absolutely, yeah.
Flat
And
Earthers, yeah.
yeah, and
If
if you
you're
look
in Muon, the
carefully,
Earth
yeah,
is
this shrunk to the size of 2 football pitches. So
flat. Amazing, love that. Brilliant. So let's have a look at the questions. Nice, so we've got one that seems quite popular, asking about how superconductors actually work. So how do they work on the sort of subatomic level? Can you answer that? Can we answer that?
sort of. We can answer it for some of them. I've got this animation here, which I've stolen from other outreach work that we do. And you can imagine this here as like, if you think of metallic bonding, for example, you've got your atoms, which are positive, or your nuclei, which are positively charged, sitting in a lattice, and you've got your electrons being shared around the outside. And these positive charges here are the nuclei. So what essentially happens is we fire an electron through them, or an electron moves through them due to current. And as the electron goes through, the positive charges kind of are brought towards the electron, and so another electron coming along will see a kind of like a more positive charge and essentially get a free ride moving across. Now this does have a lot of problems, this description. Actually, the answer of how superconductors work is a really, really difficult thing, and it's a subject of modern research, which we often use muons for, as he talks about. But yeah, truly understanding what they're doing at the subatomic level is really, really difficult to understand.
Right, so it's all about those electrons kind of moving through as pairs.
That's it. That's exactly it. Yeah.
Right,
yeah.
rather than on their own. So obviously in a conventional conductor, you almost have kind of like the sea of electrons is kind of the model that we use, right? That just travel through and they experience the resistance. But here it's them moving as pairs that kind of counteracts that resistance.
Yeah.
Nice.
That's it. Yeah.
And like you say, it's still not fully understood, because I heard you say at the start when you're answering that we can explain it for some of them, but not all of them. So
yeah, absolutely. Yeah. It's still a big mystery in physics. And another mystery, of course, is what's the maximum temperature we can get a superconductor up to. And if I show you this graph here, this shows you our progress so far with superconductors. And this is the year they were discovered on the x-axis, and the y-axis is the temperature we have to cool them below for them to become superconducting. And you can see as time goes by, we are managing to get that transition temperature higher and higher, but we're still, about 200K, and that's, crazy high pressures, which, won't make it practical. So it's still a big area of current research.
Awesome. So maybe some of you guys listening in today might end up doing this research in, I don't know, 5, 6, 7, 8 years.
Yeah.
Cutting edge stuff here. Fantastic. Amazing. So another question here, which I know you actually glossed over in the talk because we're running out of time, but is how do we produce muons?
Yes. Oh, good. I'm glad you asked that. So I've got videos to show you. Okay, so we use something called the ISIS synchrotron. The ISIS synchrotron is like a big particle accelerator, which is in Didcot, in this little place near Oxford. And essentially we do this. We've got this here, which is a linear accelerator. So we get protons, we pass them through this accelerator, which accelerates them, I think, up to about 70% of the speed of light. But I'm not sure, don't hold me to that. And then they go round and round in the synchrotron, getting faster and faster, being accelerated by magnetic fields. Then they smash into a graphite target, and the graphite, the same material in your pencil. And from that, they create, I believe, pions, and the pions then decay into muons. And I do have a flashy video for you as well. Okay, so initially the H- ions get accelerated by the linear accelerator, and then they whiz round this synchrotron here, this little circle, where magnetic fields accelerate them to go even faster. And then some of these are taken into the target station, where they smash into a graphite target, and the graphite target creates the muons. And those blue lines there are the muons going into the instruments where we can do experiments with them.
Cool. So we actually produce them however many miles, 20 miles down the road from Oxford. Is it 20 miles? It's pretty close, isn't it?
That's it, yes. There's only 4 places in the world that do it. Oxford's one of them. There's one in Canada, one in Switzerland, one in Japan, and that's it. So it's a really niche area of research.
Wow, nice. So if you're interested in this sort of research, Oxford's a good place to be doing it.
Definitely, yeah.
Fantastic. So thinking about it as research, so we've got a question here asking, do you do materials or physics? So does this fall under physics or does it fall under kind of material science?
Well, the answer is both. So I'm technically part of the Department of Physics, but a lot of people are in departments of materials in other universities, and they use this technique. So I think with all these things, that the distinctions between all these subjects are all man-made. So yeah, I think in this sense, materials and physics are pretty much the same thing.
There is a lot of overlap between the two that I don't think a lot of people realise. So could you go into your research, I suppose, if we're thinking in terms of degrees? So you did a physics degree, right?
Yes.
Do you think you could also go into this research from doing a materials science degree?
I'd imagine so, yeah, because I think if you do materials science, you'll still understand magnetism, you'll still understand how electrons and atoms work inside materials. Yeah, sure, using muons and stuff, but actually, the muon to us is just a heavy electron. There's nothing special. You don't use any of the particle physics properties of the muon, really. Yeah, so you could definitely go into this by doing a materials science degree.
Put a nice different perspective on it as well, I guess. Great, thanks for that. Let's see, is there one more question? Let's see. Oh yeah, okay, so this is a good one. So you talked about muons decaying, and we detect their decay products to kind of go back in time and figure out what the muon was doing. But we've got a question here asking, what does a muon usually decay into? So what are the things that we are detecting?
So the muon mainly decays into, so if we're doing anti-muons, they would decay into positrons, which are anti-electrons. Or if we're using normal muons, they decay into electrons. As detecting electrons is really, really easy. Most things, electrons, there's charge, so we can just get some sort of, charged plate or whatever and do it that way. They also decay into these other particles called neutrinos, and neutrinos are really weird and they're really hard to detect. So we normally don't even bother with the neutrinos and just focus on the charged decay products because they're a lot easier to detect and understand.
Don't let a neutrino physicist hear you say that.
Yeah.
Yeah. Great, thank you for that. I think that's probably about all we have time for today. So thank you all for coming.
Thank you very much, guys. Thank you.